the network, I better vet it before I use it in some dangerous way. Fairly simple rule to state. It has to be obeyed all over the place. You all the time, lots of bugs. EDA also is interested in this. And in general, any place where code blowing up is bad, people seem to be interested. Okay. So far I've talked about it in terms of, you build this checker and then you run it. What's typically the case is if you have a rule that needs to be checked, either someone else already had the same rule and they've already written a checker for you, or for instance, Kubernetes has already done it. They have a large suite of checkers. So they have things to look for: resource leaks, memory leaks, file pointer leaks, difficult concurrency problems, deadlock, sleeping while holding a lock, just as we've talked about. The standard pointer errors, using free stuff, using uninitialized stuff, dereferencing null stuff, all the usual bad things, memory overflows. A lot of security checkers, buffer overflows, stack smashing, incorrect handling of signed integers, which is always amusing when you see it in the real world, and a lot of data handling stuff. So they have a whole suite of things. So what typically happens is you can just have them come out, run it on the code in the morning, look at the bugs in the afternoon. You don't have to do much besides over time, if you want to get more coverage, you add more customization to say, look, this foo function actually frees memory, or this bar function actually returns null pointers, that sort of thing. Okay, so I'll just give a quick snapshot of how things look sort of in the real world. So these are how bugs are presented. And the way it works is sort of what you would want. It says, what was the bug? What are the events that make it believe there's a bug, and what the path was that was taken to cause the bug to happen? So this is a snapshot of a piece of code from Linux, as usual. So the first line, so what this says is the error message is at the bottom. It says this host thing was null, and it was passed to a function that could dereference it. And so you want to know why you believe that. And if you look at the top, you can see what it is. So it says, at its host, it's tracking at 4827. When host is null, it says this is the first event that's interesting. If we take the false path, if host is not null, we take the false path. On the false path, host must be null, and it gets passed to this SCSI set device thing. And anything that's underlined, you can click on to navigate around. So if we skip over a couple of things. If you click on the SCSI set device, you see that the first thing it does is dereference shost, which we know was passed in as null. Okay, so fairly straightforward thing. The interface looks about what you would want. What was the problem? What were the reasons that led to it? And let me click around and see what's going on. So nothing too surprising, and it seems to work fairly well. All right, so there's two things that there's actually a couple. Sorry, let's go back. There's a couple things that aren't on this slide that are pretty important. So the first is that we want to make you expect each error message at most once. So when you run the tool in the source code, you mark the error message. What happens is that gets sucked. You mark it as either a bug or a false positive or a don't care. That gets sucked into a database. And then when you rerun them on the source code, that error pops out. It will get automatically relabeled as whatever you labeled it with the first time. Now, the key thing is you don't want to do this in terms of text. So I don't want to put in the error message was at 48452, because what happened, with this variable name and this function name and this kind of stuff, what we do is we take the control flow graph, the compiler, what the representation the compiler has, which has the meaning of what the code is relevant to that error message, and we store that in the database. And what this means is that if you go and you change variable names or you add code and you dilate the code interleave to the error, none of this really matters. The only thing that's going to matter is if you change something and actually change the error itself. And the cute result of this is because we're just storing the code, the semantic representation of the code rather than its textual representation, is what happens many times is when you inspect one error message, you're going to label that one error message, and suddenly you get 4 other error messages labeled with the same way for free. So if we label this one as a bug, it wouldn't be too surprising if another couple error messages somewhere else in your system also got labeled as a bug. And what happens is that often when you have people cut and paste code all the time, and if that code has a bug in it, and they cut and paste it, they also cut and paste the bug itself. And so you see these bugs just replicated throughout systems, and across systems too, amusingly enough. Okay. The other thing is that one of the key things you really want to do is suppress false positives. And so, for instance, static analysis is doing what you're doing to the code right now, which is just looking at it and thinking about it real hard, and then after a while it just has to give up. Unless you run it, you don't really know for sure what the values of certain things are. And if you don't know that, you don't know whether certain paths could be executed or not. And so, for instance, if there's a path that can't be executed and we follow it and we find a bug on that path, that's not really a real bug because it wasn't really a real path. So a key part of static analysis is suppressing those those types of false positives, suppressing those false paths. So you can imagine all sorts of different ways that you might have to do this. And it turns out there's really only one thing you have to do that you have to do really well, but you really only have to do this one thing, which is it's called path-sensitive analysis. All this means it's a really opaque way of saying you just track constraints on paths and figure out, and you couple those to values. So what this means here is, if we look at the first piece of code, test, if we're not very clever, we run a check over this piece of code, and we say that, oh, actually, var gets assigned null, and then var gets dereferenced at the end of that test function, and that's a bug. But if you're a bit more clever and you look at this, you realize that can't really happen because var is only assigned null when parameter is equal to 0, and var is only dereferenced when parameter is not equal to 0. So the tool tracks this sort of thing. What were the constraints on something when it was in a certain state? And you can also do this across procedure boundaries. At this point, it's called context-dependent path-sensitive analysis. In the second example, if we're stupid, we run a tool over test call, and we see that if var is null, we call test callee, and we see that test callee dereferences var. But if we're a bit more clever, we notice that, well, actually, var is only dereferenced when parameter was 0, and we only pass a null pointer to test callee when parameter is 1, so this can't happen. So again, the tool is going to suppress this for you automatically. And it turns out if you do this and you do it really well, that gets rid of about 90% of all false positives. So it's a good thing. Okay, so a couple of questions. Is this product just for C and C++? C and Linux? No. So it works on C, C++, Java. There's a beta version. Anything where you have a compiler that can do some sort of reasoning about source code, you can do these sort of things. I'm just using Linux analysis, Linux examples to keep it concrete, but using Linux so we don't get sued. And does aliasing information go into the database? No, you wouldn't. What goes in the database are the events. Well, yes and no. What's going to go in the database are the events that were relevant for the error. So to some degree, you don't really need to track the aliasing for that. To another degree, you do. So the stuff that's relevant to the error message will get stuffed in the database. Everything the checker considered, all the reasons it believes that there's an error, will get pulled into the database. Everything else it doesn't pay attention to. Some other lints, yes, allow annotations. Do you think this is useful? So I certainly think annotations in general are allowing people to encode knowledge in their source code is useful. The trouble with a lot of these lint tools, which there's two problems. One is that they're typically very weak in terms of analysis. The other is that they demand that you annotate. No annotate, no useful results, and that's not so pleasant. So a lot of that information you can actually infer, and it looks like this is, I'll try to get to that as quickly as possible and talk about how you can actually infer a lot of stuff without annotations. Okay. So I'm gonna start going forward a bit at this point. Okay, so hybrid works pretty well in the real world. You can do aggressive interprocedure analysis and find deep errors. The main thing you want to do is a lot of path-sensitive analysis to kill false positives, and it seems to work pretty well in the real world. Fairly big companies seem to like it pretty well. And so the next thing I'll talk about, I guess very briefly, is belief analysis.